everyone, thanks for the quick introduction. I think the PhD was in 2008, but everything else fine. Let's get back down to earth. I'm Jan Benhelm, leading the marketing activities, and in today's instruments session, I want to give you a quick introduction to Zurich Instruments quantum computing control system, and maybe more exciting, give you two news that hopefully will raise your confidence in our approach to scaling systems to 100 qubits and beyond. Let's get right into it. And you've seen that before, of course, what you have to do in order to build a quantum computer, the full stack. And there is, of course, the physics package down here where all the magic happens and where there is a lot of exciting publications waiting for researchers. And then there is the applications and algorithms up here. Also nice publications waiting, but also that's where the business is. And the area in between is often considered less exciting to scientists, of course. And that's where we actually live in, and our quantum computing control system. So we connect the qubits, transmon superconducting qubits or spin qubits with higher software layers in this stack. And to get a bit more concrete here, let's have a look at the world's first commercial quantum computing control system that we introduced in 2018 and what we refer to as generation 1. So there is, first of all, the signal generation side for qubit control. So we have AWGs in the baseband and also IQ upconversion units that work with a local oscillator. And then there is, on the detection side, qubit readout, this quantum analyzer that we developed together with Leo Di Carlo and his group in the TU Delft to provide real-time state detection, fast feedback for up to 10 qubits in a multiplexed fashion. Also, this instrument operates in a baseband. So depending on the setup size, people would pick different amounts of each of these instruments to supply their apparatus. And then on top, there is a programmable quantum system controller that serves for the synchronization of the entire setup so that the whole thing ticks like a Swiss clockwork. And it's also in place to do real-time data processing, data transfer. What does this mean? So when the quantum analyzer detect qubits, make measurements, they report back to the system controller, which then can digest the data, process the data, and redistribute them back into the system. Last but not least, we have very advanced instrument control software called LabOne, providing APIs for automation and user interfaces that visualize results and make it easy to get started. But also in this generation 1, it's also the case that the entire setup orchestration is still done by our customers. So they would have to write some additional software to make all the instruments work together in an harmonious way. Now let's have a quick look what our customers actually achieved over the last couple of years. So we have many installations around, work very closely with Quantum Device Lab here in Zurich, of course, the people in Delft. We have Quantum Inspire, already mentioned this morning. So the first European quantum computer in the cloud with their spin and transmon qubits, both running with our hardware. We have Berkeley Lab, IQM Finland, Intel, all of those are bigger setups. And some of the recent success stories over the last 2 years include real-time precompensation, for instance, to improve gate operations. Then we have a very short 4 nanosecond single qubit gate done by IBM with our HD-AWG, and the first Surface 7 code implementation recently done by ETH in Zurich. This is very exciting, and there's also some pressure coming that we move forward with this. So let's have a quick look at our roadmap. And there we see essentially two edges. And there's the technology thrust, which is down here. And this is actually where the majority of the setups are today. So most labs today have setups with 1 up to 5 or 10 qubits at most. And they are very much into improving the basic technologies, improving coherence time, gate fidelities, materials, and how all these things work together. And then on the other side, we have the few big companies and consortia and so on who have the money and the resources to really drive the scale up. And this is obviously also where all the public attention is. So the breakthrough by Google announcing quantum supremacy and so on captures all the attention. And in the rest of this presentation, I want to give you two new announcements, what we do in order to support these efforts. We are part of some of these consortia. Open SuperQ was discussed this morning already. And the first announcement is on the hardware side, on the instrumentation side. And this is the very recent introduction of the SHFQA Super High Frequency Quantum Analyzer, which we consider as a next generation instrument. Why next generation? And this includes the microwave generation and detection up to 8.5 gigahertz. So we'll not have to deal with external local oscillators or mixers. It's also a very compact design. So it reads up to 64 qubits in a single instrument. So there's a 2 and a 4 channel version, and each channel can detect up to 8 qubits. It integrates seamlessly in our central controller approach over Z-Sync. So this is the information transfer lines between the instruments. And obviously we did give a strong effort to, again, improve the performance to achieve optimal signal to noise and also get down latency. Now, we also have to look at the economic side when we talk about scaling, and what matters here is to reduce the price per qubit, also to control the qubits with less instrument volume to still get everything in one lab or even better in one rack, and of course have less boxes and less instruments, less different instruments around to reduce the control effort and to get down complexity. I think the SHFQA is a very important step in that direction. So we definitely improved on all of these aspects. And let's have a look also on the feature and performance side. So one feature that we added now is multi-state discrimination. Some qubit families, this can be very beneficial if you can not only detect 2-level systems, but also 3- and 4-level systems. Then on the performance side, we changed actually the technology approach, how we generate and detect microwaves. So instead of using IQ mixing, we go to a double super heterodyne frequency conversion scheme I come to in a minute. If you look at the spectra here on the right, you see a clear difference when it comes to spurious frequencies around. So there's less frequencies and they're also much lower in amplitude. Another very important aspect to this is also the stability. So on the lower right-hand side in this pane, you see a temperature jump introduced 10 degrees. So from 20 Celsius to 30 degrees Celsius. And there's practically no change on the SHFQA side, whereas at the IQ mixing, you see a dramatic difference. Sorry, go back. You see a dramatic difference, which is of course very painful if you have to frequently recalibrate your setup and project it basically in an operative state. Now, on the signal processing side and the way we handle the data, there were also improvements. So we have complex integration now, there's digital mixing, and all of this comes together to improve to lower latency, higher fidelity, and more efficient workflows. Let me spend a few words on the new frequency generation scheme, so the double superheterodyne frequency conversion. So the way it works is on the detection side, imagine you start with 8 gigahertz, you get the frequency in, you filter all the higher frequency components out, you mix the signal with 20 gigahertz, which gives you like a 12 gigahertz intermediate frequency, and that allows you to cut away all the higher frequency components which are way out, and also the lower frequency components that might disturb the detection. After that, you go back and mix down to 3 gigahertz again, which you then can conveniently digitize with a single ADC. Now, from our perspective, there is so this is a very well-established scheme also for RF spectrum analyzers. So this is usually taken when you need good linearity, when you need tunability, and a very clean spectrum. There is an alternative approach, which is to operate in higher Nyquist zones using direct RF, for instance. We looked at that very closely, and with the present technology available and also looking at the requirements from our customer, we truly believe that we found a better trade-off with this double superheterodyne frequency conversion scheme. At the end, the truth is always in the lab, and that's why I'm very excited to show you some very preliminary results. So this was an attempt to see how well the multi-state discrimination works and how the instrument and the prototype integrates into a setup. And I can say this works very smoothly, but you see here in this graphic that there is still a significant overlap over from the different point clouds here into the neighboring areas, which reflects in imperfect state discrimination fidelities. And the reason here is not in the SHFQA. It has exactly the same performance as other analyzers, but it's the missing tupa, so no parametric amplifier, so there was too much noise around at this time, at this setup, and this is something we definitely want to improve. And I hope we can join these results at our launch event, which is scheduled in November. So if you're kindly invited to join in there. If you want to register, we recommend you just type SHFQA in Google, which will lead you directly to our product website, where you can join in for this virtual event again. And now I think is the moment where I cannot resist to say there's one more thing. And in our case, this is software. So we are very proud to announce that we significantly extend our LabOne instrument control software package by a part which we call QCCS Software. So the former LabOne software was basically controlling individual instruments through APIs. This is something you see down here in the lower right-hand corner. And on top of this, we build a structure based on Python and JSON, where people can use a DSL to define their setup and also their experiments in a human readable way, which is then translated into an experiment JSON file, which contains all the information that is needed to run the entire experiment series, which is then interpreted and transferred by our QCCS compiler, which decides which part can be directly run on the real-time environment, which is here to the right-hand side. So this will be directly programming the entire hardware. And then there will be parts which cannot be done fully in real time, but in something what we call near time. So it's still fast, but it's not sample accurate. And this is also the place where we can integrate third-party drivers and hardware. Like if you want to do an experiment where you shift the frequency of a local oscillator because you have to scan over a very wide range, this is the way to go. So obviously there's also an opportunity to get back the results and pipe them back to the higher software layers. Let's have a quick look how this DSL is structured. And this goes like we start with a definition of the entire setup. So what are the different instruments involved and what are the connections? Then there is a section which defines the individual signals. So we say signals whenever we mean a line that goes to a fridge, for instance. And then sections are compartments of pulses on different lines, which can be shifted around, and then the individual pulses. Now, once all of these things are defined, you can start putting them in an order and introduce the notion of timing. And finally, you can execute the experiments and get the results back. Now, let me summarize the motivation for all of this. And I think I want to quote Frank Wilhelm Mauch from this morning, who said that he, as a theoretical physicist, has now full confidence and likes the fact that his students can actually run the systems using our software. This is very encouraging. This is very motivating to push forward further along those lines. We want our customers to use the entire setup basically like a single instrument, and the software should take care of the whole synchronization, orchestration, and so on of the entire system. Another aspect is efficiency. So the software should take care of how to make best use of the experiment time, so to minimize the time in which the experiment sits there idle because something has to be reconfigured or recalibrated, and so on and so on. I think the ultimate goal will be to get to a point where our software connects to higher layers in a way that people would just plug it in and don't even notice that they use Zurich Instruments and hardware and software, but I think that is still some way to go. Now, let me conclude with a slide with a very basic experiment. So this is the racks you see behind me, which we assembled this week. 28 instruments controlled by the QCCS software. All instruments run in full synchronicity. And we took the pleasure to make a very simple demonstration here. So like a Ramsey experiment. So you see there is 2 pulses with varying distance. So it's like the waiting time in the Ramsey. And then you have the readout pulse here. Let me start this little video here. So we switch on additional instruments as time plays. And you see how the different pulses add up. All the channels are connected to one scope at this stage. This is not quantum. It doesn't prove full phase coherence, but we have other means to measure that. And it was, I think, great fun to actually have all this set up and to see it in full operation. This is for the experimentalists, because we believe the best results are done by night. And with that, I want to close. I hope the presentation sparked some confidence in you and gave new inspiration in our ways how we intend to scale to systems with hundreds and more qubit. We would be very excited to learn more about your requirements and hope to see you in our launch event November 17th. Thanks for your attention.